get us started. And I notice there are quite a few people who we've been having rather in-depth discussions with. And so this presentation is not really intended for them, but for everyone else to try and get external feedback. Okay, so next slide. Great. So my goal is that Makan had asked me to say something inspiring about quantum optics. So I'm going to give a historical overview of quantum optics in 2 or 3 minutes, and then discuss entanglement also, and why that has been extremely interesting from both a fundamental physics point of view, and now more recently for an applications point of view. Discuss why doing experiments in space is quite interesting and leads to a number of possibilities that would be impossible otherwise. And then a quick introduction to the Deep Space Quantum Link Science Definition team that have been looking at these problems for the last, basically since January. And then finally looking at just a little discussion of a particular example of a type of experiment we might be able to do. Okay, next slide. So I'm going to maintain that basic experiments in quantum optics have really led our understanding of physics in many ways. So starting from very simple one-photon experiments like the double slit experiment, of course, we're all familiar with. The Flieger-Mandel experiment was a really interesting one where they took 2 single-mode lasers, attenuated them to the single photon level, and we're still able to see interference between them. And then quantum eraser is basically a general sort of experiment where, for example, you have 2 slits, but you have information that tells you which way a particle went through the 2 slits. But if you can erase that information, you can recover the interference. And if you, next slide. So the reason these are not just isolated experiments, but they really teach us about other things. For example, of course, now we do experiments with atom interferometers and other matter wave interferometers, basically the same sort of phenomenon that goes on in the double slit experiment. The Flieger-Mandel experiment is basically the precursor of interference between atoms falling out of 2 Bose-Einstein condensates. And the quantum eraser really teaches us all about indistinguishability and entanglement as what is controlling whether or not things are able to interfere. So that's at the single photon level, and really all of those have, I will say, what would I say, classical analogs. So just within Maxwell's equations, for example. Things get a little more interesting if we look at the 2-photon case. So next slide. So there are a number of different effects. There's the Hanbury-Brown twist experiment. Actually, just hit the next slide. I'll discuss each of these as we go. So in that case, of course, we look at correlations, and we see that photons that come in a single mode are likely to be a bunch if they're coming, say, from a thermal light source. But now we use those measurements, the measurement of the so-called G2 correlation function, as a way of calibrating the quantumness of different light sources. So if we have a single photon source, then we basically get a G2 value of 0. So it's a way of telling us how useful a source might be for quantum information processing. In the sort of, in some sense, the reverse of that is the Hongo-Mandel interference experiment, where we take 2 photons and we mix them on a beam splitter. And if those photons are indistinguishable from each other, then the bosonic nature of them will cause them to bunch together in the output of that beam splitter. And then finally, maybe the most intrinsically quantum mechanical of all of these is looking at entanglement, which leads to non-local correlations. Okay, next slide. So let me just talk briefly about entanglement. I apologize that this very first example is as simple as I could get it. So of course, if we have more than one quantum system, we can talk about states either where the total wave function is just a product of the individual wave functions of those 2 quantum systems, or in which case it's not entangled, or we have the case where we can't write the total wave function as just the product of the 2. And my favorite example, which is maybe relevant for space anyway, is that I have some atom that's sitting out in space, it's excited, and when that atom decays, it emits a photon. And if we hit the click button here, I guess maybe one more time. So it decays, and the photon goes off in one direction, and the atom has to recoil in the opposite direction. But because the photon can be emitted in any direction, and the atom can recoil in any direction, really we have this entangled state between the momenta of the atom and the momentum of the photon. So it's kind of the simplest example. And then, of course, when we look out at the sky and we see that photon one way of interpreting this is that we collapse the wave function, and suddenly the atom has acquired the momentum as though it's been going in the opposite direction the entire time. Next slide. So entanglement is really the quintessential quantum mechanical feature, the one that really separates it entirely from classical lines of thought. And so this particular example that I gave is not really one that's very controllable, not really very usable. It's difficult to do precise experiments on it. Next slide. So let me just talk for a minute about the type of experiments that we can do. For example, when we can make pairs of photons that are entangled with each other. So this is one way of making a polarization entangled photon pairs where I have a nonlinear crystal. I send in high energy photons. Occasionally those split into two daughter photons. And what I've shown here is one crystal that has a probability of creating those two photons where one is horizontal and the other one is vertical, and the second crystal where the roles are reversed. And in this way, we can create photons that are in a polarization entangled state. So I've written one example of that here, HV minus VH, and where H and V are horizontal and vertical polarization. And if we write that actually in any basis whatsoever, the two photons will always have opposite polarizations. And this is the analog of the spin singlet state that is hopefully familiar to all of us. Next slide. So the key feature is, well, next click anyway. The key feature is that each photon doesn't have any definite information whatsoever. So each photon is completely unpolarized. And yet we see that there's perfect correlations between the two photons if we look at them in the same basis. And in fact, those correlations are stronger than anything that could be described by any so-called local realistic model, or what I might say is a commonsensical model. And that we can detect by doing a test of Bell's inequalities, and the fact that we get a violation of that means we can disprove the possibility of any local realistic theory explaining these correlations that we get. Next click. So those experiments, the violation of Bell inequalities has now been seen in many experiments, and fairly recently there have been experiments with so-called all of the loopholes closed. For example, looking with very high detection efficiency and having the measurements be space-like separated. But really, there are still a number of experiments that would be interesting to do, and I'll talk about that in just a second. Next slide, next click. We've tested out to a total length of about 1,200 kilometers. That was a recent Chinese satellite experiment. Next click. And I think one of the reasons that this is now being particularly interesting is just as some of the previous experiments, like the Hanbury-Brown twist experiment result was used for doing intensity interferometry, now we're starting to see entanglement as a critical resource for many quantum information protocols. So for example, you can do very secure quantum key distribution with this. You can use those entangled photons as a way of doing quantum teleportation or entanglement swapping. That's sort of what's shown on the diagram on the right here, where we have two sources. And if I can take one photon from each of them and do a particular measurement of them, so-called Bell state measurement, that will then entangle the two outer photons, which have never talked to each other. And that can then be used for building up quantum networks, doing distributed sensing and computing. Okay, next slide. So why do we actually need space in these sort of experiments? Well, there are many experiments where having much longer baselines would be very interesting. So as I mentioned, we've only gone out so far to about 1,200 kilometers, but you could imagine an experiment where you have a satellite in MEO and could connect transcontinental stations, doing teleportation between them. If we want to connect sensors across the entire planet, we need to go across the diameter of the planet. If we can go scales of the Earth to Moon distance, that gives us a long enough time of flight where we could do, for example, a Bell inequality test where the humans can make the decision of what sort of measurement to make. And then probably the longest distance we could conceive of with current technology would be the Earth to Moon distance. Also, if we're in space, we can have different inertial frames because the photons, the sources and detections can be moving quickly relative to each other. And then finally, there are experiments where we would like to use the different gravitational potentials that can be realized in these space-based experiments. Okay, next slide. So the deep space quantum link was looking toward to try and study what sort of experiments we could do using these, what will I say, experiments that have long baselines, relativistic motions, and different gravitational potential energy configurations. And I'll just jump down to the bottom line of this, which that it's very demanding, the technology performance requirements for these, but in a way that's a good thing because exactly those same performance requirements are what we need to try and set up, for example, quantum links and quantum networks in space. Next slide. So the DSQL team came kind of from all over. Next slide. There were several core members, myself, Jason Galicios, Thomas Yanavine, Lisa Werner, and Bela Ku. We had only one face-to-face meeting before COVID hit, and then quite a few meetings after that. But you'll see that there's certainly more than 5 people on this little photo here. And if you hit the next slide, that's because we had a large number of extremely helpful external advisors helping us out with that, and including people with a local organization like Macan and Ulf Israelison, and with the NASA lead of Brad Carpenter. Next slide. So we looked at a number of different experiments here, including trying to do teleportation over long baselines. And in fact, even just this morning, we were talking about the possibility of trying to teleport from a quantum memory, say in space, down to a quantum memory on the Earth. Experiments to look at gravitational dephasing or decoherence, testing Bell's inequalities over very long baselines, both because we can have these experiments with the different frames of reference, and also the possibility of having humans being able to make the random choice in these tests. And then just the last one I'll spend just 2 minutes talking about are these tests of the equivalence principle, so-called COW tests. So next slide. So, okay, next slide. So the original COW experiment used neutrons where there was an interferometer where there was one path at one altitude and the other path at a slightly higher altitude. And because the neutrons have a different gravitational potential energy, you would see a different phase shift depending on whether the neutron spent most of its time on the bottom path or on the upper path. So we could now consider a space-based experiment where we have a much longer difference between those. And what I've shown here is just an example where, for example, we could do this using 2 time bin states. We create both an early pulse and a late pulse on the ground, and then send that up to the satellite. And you look for interference between the photon having gone the short path on the ground station and the long path on the upper station, or vice versa, the long path on the ground station and the upper path on the and the short path on the upper station. And that will then be susceptible to these general relativistic shifts. And in particular, if you have very long delay lines, you should be able to look at both general and special relativistic effects. And one thing that's interesting about this sort of an application is because the satellite can be quite far removed from the ground, little g, the acceleration of gravity, is actually different in those locations. And so this would be the first direct measurement of quantum interference where you're taking into account this curved spacetime, or the tidal notion of the metric. And then last slide here is that you could think, just to get, again, a notion of how one might do these experiments, you could imagine a satellite which is having the source and sending down the photon in one of 2 different time bins. And again, you're trying to interfere between the early photon taking the long path in the ground interferometer and the late photon taking the short path. And because the satellite, for example, is moving toward you, when it's coming toward you, those pulses are spaced closer together. And when it's moving apart, when it's moving away from you, they're further away. And in fact, you won't necessarily see any interference at all unless you can correct for that, that Doppler shift. And you could imagine doing that experiment then, and most of the effect is what I might just call a classical Doppler shift, just from the fact that the source has moved in between the time it's emitted the first and the second pulse. But in addition to that, there would be a relativistic effect just from the time dilation effect in the source itself. And you could pick out that sort of an effect, and also the general relativistic effect that the clock is moving more slowly, basically by doing a very careful measurement of the error signal. if the time bins are only separated by, say, 1.5 nanosecond, that would be very difficult to measure. But if instead you had time bins separated by something like 150 nanoseconds, or even more, if you had some sort of a quantum memory, then you could start to much more precisely measure these relativistic effects. So that was the sort of experiments that we looked at in our discussions. And last slide. We certainly look forward to hearing any questions you might have or any other suggestions you might have for related sorts of experiments. And with that, I will turn it over.
That's great. Thanks, Paul. So, Kristen, next it would be Thomas. Thomas has prepared some slides. Great.
Should I just share my PowerPoint from here because I sent a PDF yesterday, and or is that, would that be okay?
Hi Thomas, this is Kristen. It's if there's additional for example animations or something in your slides, we can make that happen. But for in the case of time, it might be easier to just continue on as so.
Yeah. Okay. Okay. There might be some text on top of other text, but it's okay. Yeah. Indicate. Yeah, we're short on time.
Okay.
Okay. Well, thank you very much. So let's go ahead. So yeah, thank you very much for having me today and being part of this discussion. And I'm also excited to be a part of this Deep Space Quantum Link initiative, and it's very interesting. I'd like to just give a few perspectives on the status of satellite-based quantum communication and also where the Canadian project, where we are at the moment. And this could be maybe a good baseline on talking about, or for this discussion, because it gives a bit of perspective on where the technology is at the moment. Let's go to the next slide, please. Next page, I guess. Right. So for a lot of the activities that we are looking at, it's about establishing a quantum network, a global quantum network, right? So this quantum internet, as it's often also referred to, is kind of this envisioned future grid which will allow to share and transmit qubits or entangled bits seamlessly through a multi-user network, right? And so like in extension of today's classical internet will essentially allow lots and lots of users or user devices to share quantum information. And the ultimate use case for such an quantum internet, is, for example, interfacing between quantum computers, right? Let's say if a user wants to, link up with a quantum computer for their computation, they might want to send quantum information rather than the classical data to the quantum computer service provider. Or if quantum computers were supposed to interface to let's say, join up their qubits and do a much better, much bigger calculation, for example, quantum internet will help dramatically to enable those kind of aspects. Now, the quantum internet, of course, is a long-term vision, and like it's outlined in this diagram here from our colleagues at Delft University, there's still many steps that have to be looked at or accomplished before this is actually really feasible. Right now, the demonstration and implementation and the technology is more at the lower level of point-to-point networks, or what they also called prepare-measure networks, and where essentially quantum key distribution, for example, can be implemented, or some other protocols, but it's still a way to go before a true quantum internet is doable. Now, let's go to the next slide. Why satellites? So the point is that with this quantum repeater, we need entanglement. So they need entanglement distribution channels, which can cover large distances between the different nodes. And satellites will play a major role in this activity, because the long distance transfer of these entangled states on the ground is limited, right, by optical fiber, or in some cases even it's difficult to have repeater nodes too close to each other, such as think of transatlantic cables and such, right? So satellite links will definitely be a part of such a network. And here are just two examples of some recent studies from our own group with Christoph Simon in Calgary, and also more recent from Daniel Oy's group in Strathclyde, on how maybe quantum satellite links and quantum repeater nodes might go hand in hand and help, form a long distance backbone for such a quantum network. Next slide, please. So quantum communication in space is a reality. So since 3-4 years actually. So the Chinese mission was already mentioned. It's the groundbreaking work by our Chinese friends led by Jianwei Pan, who demonstrated various milestones such as the distribution of entanglement over 1,200 kilometers. They implemented quantum key distribution, teleportation. They also did intercontinental QKD, for example, such as between China and Austria, and where they encrypted a video link conversation using QKD. And so many more activities are going on actually. But there's also been other dedicated space hardware, such as from Japan, right? They had their Socrates mission where they demonstrated a QKD-like emitter, a test system, or very notable is the group from Alex Ling in Singapore, which demonstrated photon sources for correlated and also more recently entangled photon pairs on small-scale satellites like CubeSats. And there's actually many more missions underway, way more than could fit onto this page. So it's an exciting time right now because so some time ago this was still a lonely field, but now there's a lot of activity happening. So next slide, please. Including okay, I should also mention I thought this was really nice. Our friend Jianwei Pan was actually highlighted on Time magazine 2018 as in the category of pioneers in the top 100 people of the year, and I think that's really exciting. It shows that a quantum physicist can actually have a real impact and be noted by essentially the world, right? So it's an amazing accomplishment. So let's sorry, next slide, please. In Canada, we're working on a mission called KeySat, Quantum Encryption and Science Satellite, where this is essentially the primary function of this satellite will be a quantum receiver for detecting photons along their polarization and keeping the sources, the emitters of the photons on the ground. And this is interesting because while the generic quantum receiver is a relatively, let's say, straightforward or established, let's say, piece of technology, we envision a lot of scientific and also, let's say, communication experiments to be done by tweaking and improving the ground segment. And that is why we chose this approach. So you can see here just a block diagram, very schematic, simply speaking, it's a so-called Bob module. So in QKD lingo, meaning the photons enter a filter, a spatial filter, and then are coupled through a set of beam splitters to measure the 4 different polarization states: horizontal, vertical, diagonal, anti-diagonal. Next slide, please. And I mean, just to illustrate some of the technology developments that we had to go through for this project is so over the essentially past decade, at my team in Waterloo and with partners, primarily in Canada, industrial partners and also agencies, we've been looking at the hardware and actually also software required for this, building, detector systems. We did radiation testing. Environments are important. We did optical design, optical development and demonstrations. And on the right-hand side, you can see some pictures of our prototypes. At the top, we have a complete optical assembly, including fine pointing and everything mounted on a pan tilt mount. On the lower picture, you can see a detector module, custom built with very nice silicon ABDs in a thermal vacuum chamber, actually for undergoing some TVAC cycling down to -80 Celsius. and actually several other activities. And right in the center, you can see two of our group members installing this hardware on an aircraft, actually, of the National Research Council in Canada, where we performed a demonstration of this technology from a ground terminal, a ground transmitter, which is, as you can see behind me here, and to this aircraft. So next slide, please. So here's just some impressions of that experiment. And we were able to demonstrate not just this transfer and that the technology and the concept worked in principle, but also just demonstrating the logistics around and planning around such a mission was actually also quite a bit big accomplishment and a step. So since then, I should say the mission has, like I said earlier on, it's a fully funded mission. The anticipated launch date is late 2022 or early 23, and from there on, experiments will start to progress. And so next slide, and I think it's also my last. Great. And I know Paul already delved into these points and questions, and this KeySat mission is only a first step towards the bigger picture of studying long-range quantum entanglement, quantum distance, long-range networks, but it does connect to the case for quantum entanglement in science in space. And one point I always like to make is that the Earth has a diameter of around 13,000 kilometers. So even if we think of ground networks, even if we have the best possible quantum repeater network on the ground, the distance between the entangled partners or particles will be limited by this diameter of the Earth. So it's actually an interesting question of is it interesting to look at larger range entanglement or quantum states? Think of Earth-Moon distance, which was mentioned already, which is approximately a light second of distance. And it allows some very acute and interesting experiments, such as Bell tests, where human observers are actually providing the random input for the observer for the polarization settings. All of this fits into the bigger picture of studying, further studying the interplay of quantum mechanics and relativity or relativistic scenarios, where we have gravitational, we extend entangled photons over gravitational differences or distances, potentials, I should say. We have maybe relativistic motion involved with satellites, which are moving quite fast, and just simply the large distances. It was gravitational decoherence is there. So just looking what else I wanted to say about this. I think it's a very exciting topic and an interesting field. And hopefully will trigger a lot of interest. And again, I would like to draw reference to the Deep Space Quantum Link, which is led by the JPL NASA team, and it's very exciting to brainstorm and think about bringing quantum entanglement further than our Earth and going outside of
registered for this workshop, I was able to see the comments that you put in the registration. They asked you a question like, what are you particularly interested in? And so I found several that were really interesting, and so I wanted to call on those people to maybe expand on their concepts a little bit. And also, as I noted, because we started late, we're going to go a little bit later. So we'll end the meeting in about half an hour, 35 minutes from now. So 40 minutes past the hour in your local time. Let's see. So Lisa Werner from DLR. Lisa, are you there?
Sure. Yeah.
Great, Lisa. So maybe you could share with the participants what your ideas were along these lines.
Yes, so of course, in this session, the idea goes mainly along the line of expanding distances. So what Paul and also Thomas have been talking towards, trying to enable something on an Earth-Moon basis. And I guess so. There's of course there's a lot of scientific cases that can be made for that, and those have been discussed. And all of those I think are worthwhile doing and worthwhile trying. And on the other side, what I would like to also stress is that this, of course, comes with a lot of technology developments that need to be done and need to be prepared in order to do so. Not the least of those, which I think Paul called technologically challenging, is to actually establish the link and being able to have enough photon count over these distances. So this is for sure something technology-wise that I think is very, very important for these kinds of missions. Also, the quantum memories that have been discussed could be very much worthwhile for a lot of those. So these are really the parts technology-wise that I'm very, very interested in and that I think are something that we should definitely take into account for this Decadal, not only enabling these very interesting experiments, but also giving us opportunities to consider other experiments that might then rely on the technology that we have developed for these things, especially in terms of information transfer and communication. Of course, the last one, maybe one of the most important ones for me, is to continue this really nice collaboration, trying to combine our expertises on these fields and build on what has been established. And now I have to go a little bit to my personal background, has been established to Cal and BCal, and also use all the experience that was gained through that. So this is really why I'm here. That was very much top level, but I hope that was what you're looking for, Makan.
That's great, Lisa. Thank you so much. You highlighted the technology development, which is critical to making any of this stuff work. And certainly in Paul and Thomas's presentations, they recognize that. There's another side to this too, which has to do with the underlying physics of weak field gravity and what quantum mechanics would be expected to, how it would be expected to be influenced by weak field gravitational effects. And Haris Anastopoulos, who's on the line, Haris, you mentioned maybe starting a theoretical physics program dedicated to this. And if you're able to, I'd like you to maybe explain some of your ideas and share them with the participants of this call. Great. Haris, you're on mute right now. You might want to unmute yourself.
Okay. So do you see the file?
Looks perfect.
Okay. So, well, there are three sets of foundational issues. Well, at least three sets that we can test in the DSQL setup. One is the quantum field theory in curved space-time. The second is the gravitation of quantum systems. And the third is some issues on the foundations of quantum theory, essentially in the interplay between quantum field theory and information. So I will say very briefly about each of those three. Quantum field theory in curved space-time is a theory, a mature theory, developed ever since the 60s. It describes matter quantum mechanically, but gravity in terms of classical general relativity. So it has an expected domain of validity when the gravitational field generated by the quantum matter is ignored, and it has been greatly successful for theorists at least. It has gives the prediction of Hawking radiation, predictions of inflation, but no test. no direct test so far. Now, what we can do is it can be used to develop quantum optics in curved space-time. What I'm saying quantum optics in curved space-time is application of QFT for the electromagnetic field in curved space-time. At weak gravity and in absence of gravitational waves, all physics is in the gravitational potential, the Newtonian potential. And there is a nice theory about the electromagnetic field, the quantum electromagnetic field on the potential, and there is a nice correspondence that the weak gravity acts more or less like a dielectric with an index of refraction given by phi. So this, it's completely isomorphic, the description of gravity in curved space-time and of the electromagnetic field in a dielectric. So light propagation leads to phase shifts that are in principle measurable. And if we go beyond, sorry, I just, okay. And if we go beyond light, if we consider massive particles, there are a lot of questions about free fall of massive particles. Like, what is the free fall of a particle prepared in a cut state or a pair of particles in an entangled state? What exactly does the theory predict? And there are many questions that have to do with equivalence principle, how the wave packet spreads, and so on. And, well, we would like to, the space setup is the ideal to try to answer this question. So this is quantum field theory in curved space-time. Now, we have the issue of gravitating quantum systems. So this is, if we have to, if we can prepare a system in a superposition of macroscopically distinct mass densities, we have what we have called a cut state, and if this generates a gravitational field, it's a gravitational cut state. And these types of systems have been studied in the last 3 or 4 years. There is a very well-known result, perhaps, that the gravity can induce entanglement if we take a pair of such gravitational cuts. And it can also induce Rabi oscillations, and this is measurable in tabletop experiments. And of course, if you have a high quality of vacuum, it can be also measured in space, at least in principle. But there is the counter idea that gravitational cut states do not exist. This is an idea originally by Roger Penrose. And there is a mechanism, a physical mechanism, a proposal that these states might be killed by new physics. So this is the so-called Diosi-Penrose decoherence theory, decoherence model. And in principle, this can be tested at the scales of, well, it can be tested in space. Space is the optimum place where to test this. And I have to say, this is a rather far-fetched proposal, but if it is verified, the implications are really, really revolutionary for theoretical physics. There are other models of decoherence. One is the one that me and Bela Hu have developed. We have recently upgraded this model to photons. And so it is possible to predict that there will be dephasing in quantum optical experiments. So this is the second thing, the decoherence. And the third thing is the foundation of QFT. There is an old paradox, well, about measurements in relativistic systems, when the two measurements are space-like separated, the two measurement events. Because in a space-like separated events, A in one reference frame is before B, and B is before A in a different reference frame. So if you follow the usual postulate of reduction in measurements, and you try, this creates ambiguities. So, and these ambiguities have, well, they refer to ordinary quantum theory or they refer to quantum field theory, but they are there. The answer by the founders of quantum theory, well, by Werner, is that we should not take the quantum state literally. We should only consider probabilities. Probabilities are consistent, while the assignment of quantum states is not when we have relativity. Or there's another answer that there's a preferred reference frame. That is a violation of relativity. So this type of experiments that involve two measurements, bell-type tests, space-like separations, are tests of, in some sense, of relativistic quantum theory. It's related to an essential axioms of QFT, and in order to actually phrase what new type of experiments, we need also theoretical development, because QFT has not, it's just now developing a language of measurement theory and the language of information in this setup. There is a community of relativistic quantum information that is interested in this type of questions. We have been working for more than 10 years. There is an international community. Some of these questions are relevant to this experiment, and I conclude with my favorite question, which is to test non-locality with time observables, not spin observables, not discrete observables, but with time observables like detection time, time of light, and there are bell-type theories about detection time, in the sense that there is no classical theory that can give the unequal time detection probability for separated events. So this is another type of non-locality that is not so very well known. Well, it is well known. Legend-Garg inequality is an example that is well known, but it is more intrinsic to quantum field theory than standard bell tests. And this is a very short presentation.
That's fantastic, Horace. And I would just point out that, like, what he just talked about, it's purely theoretical issues, but they're directly relevant to the type of fundamental physics that NASA is trying to explore with these potential space missions. And so for the Decadal survey and the Decadal review, we're perfectly justified to propose to NASA, hey, you should make a program to fund theoretical physics research in these areas, because it's directly related to the type of experiment you're trying to do in space. So that's very, very good. Thank you. Daniel Oy, from Strathclyde University.
Yeah. Hi, McCann. Thanks for inviting me to say a few words. I think Thomas alluded to a paper on quantum memories. I just want to acknowledge the work by my collaborators at Humboldt University, and they've been involved in Decadal and other experiments that have been mentioned before. So I think that leads to my first point is, I think the development of new quantum technologies, I think they really have a possibility of impacting what we can do in space. I mean, this has been highlighted by the presentations, like for instance, in sorry, I think there was some background. All right, so. So I think the advancement in quantum technology allow us to really think about what we can do, what sort of experiments we can do. Maybe not ones which we necessarily have a good theoretical theory or a mechanism by which we could predict effects, but they may probe situations that we have not yet been able to explore. So I've just got a few things that I wanted to highlight. So I think there's two effects in entanglement that we could really think about. So how does entanglement change in propagation of quantum states through space-time? So I think that's been very well highlighted. But we can also think about how does entanglement behave at rest, for instance, in quantum memories. So for instance, entanglement which is being stored in different degrees of freedom. Does it matter whether it's stored as optical signals or in atomic coherences or maybe in nanomechanical oscillators. Maybe these effects by which entanglement, the mode in which they're stored could lead to different effects. This is somewhat in the work of some of the gravitational induced decoherence theories by, like for instance, Tim Ralph. If we look at the experiments that he's proposed, there is dependence on the degrees of freedom which the entanglement is actually being stored in. So this possibly could be explored by using different kinds of quantum memories. I think we can look at massively entangled systems instead of just simply photonic entanglement, particularly the development of nanomechanical systems and coupling of nanomechanics with optical signals, and seeing whether that could lead us to enhancement of some of these effects that are difficult to measure directly just on optical signals. And I think the last thing also is to look at perhaps not just point-to-point or bipartite entangled systems, but perhaps going to multipartite entanglement, and also looking at closed paths, or look at non-linear geometries by which we can explore the effect of gravity or curvature of space on quantum systems. So I think that's sort of a wrap up of the kind of things that I've sort of identified as possible areas to explore, which are driven by the kind of technologies that we're developing, which could extend what we could actually probe.
That's great. Thank you. Thank you so much, Daniel. Those are all really, really interesting ideas. I'd like to give Simone Delagnello a chance to weigh in. Simone, if you're available. Well, I think you went off mute. You went back on mute. There you go.
Okay. So thanks for the invitation, Makan. I do not belong to this community, at least not just yet. So I welcome this opportunity, and I would like to explain briefly what we do and see if we can get opportunities for collaboration. So I work for the Italian INFN, the Institute of Nuclear Physics. INFN does particle physics, but also does gravitational waves. We have a gravitational wave interferometer in Italy called Virgo, which is working with LIGO since a few years. What we work on is test of general relativity and relativistic theories of gravity beyond general relativity. And we do that by precise measurement positions in space using a time-of-flight technique, which is called satellite and lunar laser ranging. And this is the distance measured from ground stations to devices called laser retroreflectors, like the Apollo reflectors on the moon. So we work on the design, construction, and delivery of these space devices, the laser retroreflectors. And we partner with the laser stations. The ground segment is the so-called International Laser Ranging. Accurately at the level of centimeter with these 5 points on the moon, and we test the strong equivalence principle using the three-body system, Earth, Moon, and the Sun. We test and we measure G dot over G with an accuracy at the moment around 9 times 10 to the minus 13, the geodetic precession, and the inverse square law. We collaborate with the lunar ground stations, and in particular with the French one, well, with all of three actually, in the US, France, and Italy. And we collaborate in particular with the one in Italy because they are doing from there quantum communications, not with us, but with another Italian group, the group of the University of Padua, led by Paolo Villoresi. and we collaborate with them for the laser ranging to the new next generation of lunar reflectors, because the new generation of reflectors will be uncoated retroreflectors, which do not preserve the polarization of the incoming photons. If you have a coated reflector, then that preserves the polarization, which is what you want when you do your testing with the entanglement. So in this station in south of Italy, they have a very sophisticated polarimeter, which is being produced by the University of Padua, Villoresi et al., which can control very accurately the polarization of the photons which are sent to the moon and received back. So they do a very precious just diagnostics for us to understand if and how the new generation of reflectors on the moon can perform better than the old ones. Now, when we do these measurements, we can also test theories beyond general relativity. And we have produced a few papers with theoretical predictions by our theory subgroup, plus experimental constraints from the data about us experimentalists. And we have tested the theories like space-time torsion. There is a version of the many versions of space-time torsion which can have measurable effects depending on the parameters on the orbits of Mercury, of the Lagios satellites, which are used for geodesy and land steering, and of the moon. So, and another theory which we can test is a non-minimally coupled gravity, in which in the action functional of gravity, a second function is added in order to couple space-time, curvature, and matter. And we can test these if there are new theories which somehow introduce a Yukawa potential, which somehow can change the geodetic precession of the moon. So I'm telling you this stuff which doesn't really fall directly into your field. However, just to tell you about the technologies, the connections we have with the ground stations, and if laser reflectors in which you measure accurately the position of the moon and Mars, because we have put reflectors also on Mars, can be of use in your studies, then we'll be happy to collaborate. One last thing, I'm at the moment located in San Francisco. I have a temporary job of science attaché of the Consulate General, so I can institutionally provide liaisons with Italian academia, contacts with the Italian Space Agency, the Italian ministries. So if there is any need to create an institutional interface with Italy, it's my job here in the West Coast. So with you at JPL, I can work with you if needed.
That's fantastic. Thank you so much for that summary of the laser ranging science that's conducted, and also the offer of kind of like agency level and institutional level support. I think one thing that's obvious from looking at the type of like this deep space quantum link and the scope of that mission is that it's going to require international cooperation to make this happen, both at the technology development level and also implementing, you know, those extremely long baseline quantum links. It's like an all hands on deck scenario where there'll be room for lots of contributors. So I want to ask, you know, if anyone who hasn't had a chance to speak or ask questions, you can please do so in the chat box. We have a little bit of time left before we conclude. Let's say 10 minutes. So please, if anyone wants to ask a question. Dan Gauthier from Ohio State, take it away.
A lot of these techniques are going to require single photon detectors that work at incredibly low count rates, and they have to work in a horrible radiation environment. So Thomas and others have started to look at radiation sensitivity for silicon detectors. It looks like the nanowire detectors might be less sensitive, but then they require cryogenics around 1 Kelvin. So there's going to have to be other associated technologies developed, like in the area of making compact cryogenics. that can be space qualified to really make any of these missions work. I always find when I've been doing quantum key distribution work, it's always the detectors that limit what you can do. And I think that's going to be true here. In many cases, the sources and the control electronics, we know how to harden them, but it's the detectors. I think it's a huge hole there that we're going to have to solve to make these missions happen. That's all. Thanks.
Thank you, Dan. Let's see. Okay, anyone else? Going once, going twice? So yeah, I mean, I guess I'd like to invite Paul and Thomas to add any final comments if they'd like to at this time.
Thomas, you want to go first?
Yeah, sure. Thanks a lot, and thanks everyone for joining this session. I think it's a very exciting area. There's a lot of interesting directions here, and I think there's many exciting fields. It's not just the application space, the quantum networks. It's also this fundamental science. And like we heard, also these nice discussions on curved space time and other things, and memories in in space. These are very interesting developments, I think, and we should pursue this. I mean, we as a group of science, the science community, to push the boundaries of where where we validate and test our theories, right? And I think space, long range entanglement in space under those scenarios, I think is definitely a parameter space we need to explore in the future. Yeah, thanks.
So yeah, I'd just like to thank everyone for coming and staying up late. For those of you who are up late, I'll just say my own history. I got into physics because of Bell's inequalities and reading about it, and just the basic, very fundamental physics. And with the rush of quantum information over the last couple decades, it's been much more of a focus on, okay, how can we get to do interesting or useful applications of things? And I'm totally on board with that, and I think that's really interesting. But I think now the fact that we're entering new regimes where we can go back and continue to do interesting physics that's really new in regimes that wasn't possible before, I think it's really exciting. I mean, it's been a while. You have to work pretty hard now to get to a regime that hasn't been tested in many of these experiments, and being able to do something in a space environment where you really have distances that are orders of magnitude longer, or you have relative velocities that are much higher than anything you can do in a laboratory. I think that's all extremely interesting, and it's an interesting question what we'll find from that. It could be that we find that everything works kind of just the way that we thought it would. And I guess I just kind of harken back to more than a century ago, where they thought that physics was pretty much all wrapped up except for that little thing in the ultraviolet end of the spectrum. And well, we're pretty sure we're going to figure that out, and it's not going to be a big deal. But of course, it changed everything. Who knows if that's going to be the thing that happens here? I think it's very interesting. Both, there is a tantalizing possibility that you learn something, you get a totally different perspective and you have to rewrite all the laws. But I think even if that doesn't happen, the experiments are just so interesting, being able to look in these new regimes, and the fact that to develop the technology to do that is the same technology that you need in order to do useful things. In the same way that, people developed atomic clocks initially to do fundamental physics, and now they enable all these other things. Now they enable GPS. So being able to develop these basic science capabilities, which will then eventually enable some capability that, I guess I certainly can't think about at the moment what that will be. So hard to predict what that would be, in the same way that GPS was not really predicted, I guess, when people were first doing atomic clock experiments. So I think it's really interesting to say, what to see. It'll be great to see what we come up with if we can get some of these experiments to fly. So anyway, that's my my parting thoughts, I guess. Makan, do you have any parting thoughts?
No,
Other than
that's great, Paul.
people should email you other suggestions that they may have.
Yeah, thanks. That was great. That's real inspirational. I really liked it. I like to hear about why you went into physics. I've always liked classical mechanics, and yet here I am today talking about quantum optics. So, yeah, like now we're at the point where, you know, they're starting the decadal review process, and it's up to us as a community, as Thomas said, like us as a physics community, to tell NASA what we think the priority should be for a next space mission, right? And if doing quantum optics in space to measure the type of you know, really interesting physics predictions that Professor Anastopoulos covered and that the other speakers mentioned, if that's important to you and you think it should be important to NASA, this is our chance to write something up and to advocate for it. You can talk about things like, this is it for your white paper contribution to the decadal survey. You can talk about like the scope of a mission, right? Like Deep Space Quantum Link. You could talk about what the scope of that mission should be. You could email me and we can, you know, coordinate responses. You could identify specific technology items, like Professor Gautier talked about radiation damage in these detectors, right? Or even for that matter, fibers, which is going to be critical. And you could advocate for funding that, researching that, and solving those technical problems or mitigating them. You could propose theoretical physics research programs that contribute to all this. And you know, just from my perspective at JPL, I think there's other NASA folks on the line. The degree that we can coordinate amongst ourselves our responses would kind of strengthen the overall push. And so with that in mind, I just encourage you to reach out to me and other people that you might recognize on this call so that we can help each other make this thing happen. So thanks very much. I appreciate everyone's time and attention, and the NASA folks for getting us together after that brief delay at the beginning. So thanks very much, everyone. I'm going to say goodbye. And thank you to our two speakers. Bye.
Thanks everyone for hanging in.
Yeah, thanks a lot. Thanks, Makan. Thanks, Paul. Thanks, NASA.
Thanks, Thomas. Talk to you guys later.
Great to see.